So in the yesterday's session, we have discussed the principle behind the production of laser, and also we have studied the construction and working principle of ruby laser and gas laser, which is helium neon laser. So the three mechanisms have been involved for the production of laser: induced absorption, spontaneous emission, and stimulated emission. So initially, by the process of induced absorption, excitation of electrons or atoms takes place, and after reaching the metastable state, they start the process of spontaneous emission by emitting photons. Basically, they are incoherent, but these photons will interact with the excited atoms which are present in the metastable state. During this process, the electrons or atoms they reach their ground state by emitting similar photons. So the emitted photon is in coherence with the incident photon. So these two photons again they knock out two more photons from two excited atoms, so that the total number becomes 4, and a chain reaction is created. And in this way, a highly coherent, energetic, intensified photon beam called as laser is produced, and this is called principle of laser, and is called as lasing action. For that, you need population inversion, that is, more number of particles or atoms present in the excited state. So in general, N1 is greater than N2. The number of atoms is more in lower energy level than higher energy level. But making N2 is more number of atoms or electrons more in the higher energy level is called pumping. And due to pumping, population inversion is achieved. And which material permits this? This is called as active medium. And also to give proper direction to the laser, a resonant cavity is required. So these are the three fundamental accessories you need for the production of laser. Basing on this principle, the first laser constructed is a solid state laser, which is a ruby laser. Ruby laser, it is a mixture of Al2O3 and Cr2O3. Minority of Cr2O3 atoms are there, and the active material is Cr2O3. So initially, a ruby rod of specific length and width is placed in a quad tube, and the left end is surrounded by a fully reflecting surface, and the right end of the quad tube is surrounded by a partial reflecting surface, and a helical xenon flash tube is surrounded the quad tube, and it produces the required flash of light by a power source. And whenever the flash of light is on, then optical light falls on a ruby crystal. Chromium atoms get excited. This is the process. But flash of light it lasts for several milliseconds. Some thousand joules of energy is released. Only a part of this energy is sufficient to rise the chromium atoms. The remaining flash of light heats the apparatus to maintain the proper cooling. A cooling arrangement is there so that it maintains the temperature of the apparatus. So initially, flash of xenon light is operated, so chromium atom is excited to their higher energy state and settles at the metastable state. Then first process of spontaneous emission starts, and it releases photons, and these photons they interact with the atoms in the metastable state. This process continues, and laser is produced. The laser beam, if it is going in the left side, it has to, by using the partial fully reflecting surface, it should get reflected. Until and unless a highly energetic coherent photon beam is produced, then only it is allowed to escape through the right side of the partial reflector. So this is the construction working of ruby laser, and the disadvantage is only pulses of light will be getting. Whenever the flash of the xenon is there, it gives laser. Again, it needs some time. Again, you should operate the flash tube so that the flash will be on the chromium ruby crystal. Again, excitation takes place. So it takes some microseconds or milliseconds. So only pulses of laser can be produced by this. So this model again it is modified by another laser which is called as gas laser, and in the quad tube a mixture of helium and neon atoms, gas molecules are taken. There is a majority of helium atoms and minority of neon atoms. Now they take in the ratio of 10:1, and the partial pressures are 1 mm of mercury and 0.1 mm of mercury respectively. And in the quad tube again, as like in ruby crystal, left side is coated with a perfectly reflecting surface and it is coated with the dielectric media. The right side is coated with a partial reflecting surface and electric discharge arrangement is there. So whenever high voltage is applied to the gas mixture, ionization of gas takes place. Initially helium will excite to their higher energy levels, helium 2 and helium 3. Then they reach the metastable state. After finishing their lifetime, then this energy excited the helium atom energy is equal to can interact with the neon atoms which are there in the ground state. So these helium excited helium atoms they react interact with neon atoms. So neon atoms rise to their levels 6 and 4 respectively, and the helium atoms comes back to the ground state. Now the neon atoms they reach their metastable state and population inversion is achieved. Once population inversion is achieved, then by spontaneous emission, it emits radiation or photons are emitted. These photons they knock out the fresh photons from the excited atoms. This process continues, and millions of photons will interact with the atoms, and number of photons are released. A photon ray is produced along the quadrant tube, and if it travels in the left side, definitely it will be reflecting from the fully reflecting surface until and unless this photon should knock out a fresh photon from the excited atom. In that sense, the arrangements are made. And finally, once sufficient energy is reached, a highly coherent, energetic, intensified laser beam is produced, which escapes to the right part of the quantity. And this is called as this is the construction and working of helium neon laser. We have discussed in the last class. And one more laser is there, which is semiconducting laser. The construction and working of semiconducting laser we should discuss now. So I will present the semiconducting laser. Before that, 36 students are there. The remaining students I will be putting absent. I'm taking screenshot here. Okay. Is this presentation is visible, students?
Yes, sir.
Okay. Take the heading semiconductor laser and take the diagram first. Then I will start the explanation. Take this diagram, semiconductor laser. N-type material, intrinsic layer, P-type material. So this construction and working, you should listen carefully. Some concept is there here. Basically, a semiconductor laser, in the short form known as SCL, is a PN junction diode operating in forward bias. You know, semiconducting materials are classified as P-type semiconductors and N-type semiconductors. P-type holes are the majority carriers, N-type electrons are the majority carriers. If a P-type and N-type sandwich together, then it is called as a PN junction diode. And forward bias arrangement is if P-type of the semiconductor is connected to the positive terminal and N-type is connected to the negative terminal, then this is called as forward bias arrangement. Under forward bias arrangement, the holes are repelled by the positive plate, the electrons are repelled by the negative plate, they travel across the junction, more number of charge carriers are available in the junction region. So under proper forward bias voltage, the current will be more. This is forward bias arrangement. So a semiconductor, it is basically a PN junction diode which can be operated in forward bias. So as I said, in forward bias, the majority carriers holes of p type and the majority carriers electrons of n type, they move towards one another in the junction region, and in the junction region, recombination of electrons and holes takes place. And this recombination energy is made to come out in the form of optical pulses or laser light at certain frequencies. So this is the principle of a semiconducting laser. So a semiconducting laser basically a PN junction diode, and it should be operated in forward bias, and under forward bias voltage the electrons and holes they move towards the junction region, and the recombination of electrons and holes takes place. Whenever an electron and hole recombine, this recombination energy is converted into an optical pulse in the required frequency, which is nothing but the laser light. So this is the principle of semiconducting laser. If you want to write this three, a semiconducting laser is basically a PN junction diode operating in forward bias. In forward bias, the holes of p-type and electrons of n-type move towards one another, and the recombination takes place at the junction region. So when forward bias voltage is applied, the electrons and holes they move through towards the junction region, and in the junction region, an electron moves combines with a hole. Electron will be there in the conduction band, hole will be there in the valence band. So the recombination takes place. So whenever an electron from conduction band to valence band, when it transfers, what happens? It gives energy. So here it gives the energy in the form of optical pulses, which are nothing but the laser. So this recombination energy is made to come out in the form of optical pulses at certain specific frequencies. And this is the principle behind semiconductor laser. Is it clear, this concept, students, boys? Somebody respond.
Yes, sir.
So this is the theory. So as I said, it is a recombination of electrons and holes for a PN junction diode under forward bias voltage. But here, the ordinary semiconducting materials like germanium, silicon, these are not suitable for the fabrication of semiconductor lasers because they have indirect band gap. So what is indirect band gap? In these materials, even in the forward bias voltage, the holes and electrons cannot recombine directly with one another. So for the recombination of charge carriers, involvement of third particle, generally lattice ion is required. So lattice is crucial for the recombination of electron in the hole, and this lattice ion, it absorbs most of the recombination energy. So when even though the electrons and holes recombine in these materials, germanium and silicon, because they have indirect band gap, the recombination energy, most of the recombination energy is converted into given into lattice ion only. So laser will not be produced. But for the fabrication of these semiconducting lasers, direct band gap materials in which a whole recombination of holes and electrons takes place are used. So there are some materials in which the recombination takes place straight away. These are called as direct band gap materials. So an electron and hole can combine directly in these materials, and this recombination energy is converted into optical pulses. So indirect band gap materials generally they are the compositions of third and fifth group elements, and the examples are gallium arsenide, gallium phosphide, gallium arsenide phosphide. All these are examples of these materials. So only materials which are having direct band gap can be used to fabricate semiconducting lasers. So this also you should understand. Ordinary materials like germanium and silicon, they are not suitable for fabricating the semiconducting lasers because they have indirect band gaps. So even for these materials, when forward bias voltage is applied, electrons and holes cannot recombine directly in the junction region. For the recombination of an electron and hole, involvement of third particle is required, which is the lattice ion, and this lattice ion absorbs most of the recombination energy. So they will not produce any laser in this case. So for the fabrication of SCL, direct band gap materials in which recombination of holes and electrons takes place are used, which are the combination of third and fifth group elements such as gallium arsenide, gallium phosphide, gallium arsenide phosphide. These are the materials. So these are used for the fabrication of semiconducting laser. Please go through this slide. To have any doubt you can ask. Then I'll go. Some more concept is also there for semiconducting laser. Is it clear up to this? The 2 points are clear. The principle behind semiconducting laser and which materials are used for the fabrication of semiconducting lasers. Shall I proceed, girls?
Yes, sir.
Boys?
Yes, sir.
Okay. So you take the left side diagram. Actually, this is the basic heterostructure of a semiconducting laser. The right side one you can take later, but first you take the circuit diagram here. A simple heterostructure of semiconducting laser. Let's you take this one. Take the figure. So the first point we have discussed here is a semiconducting laser work on the principle of a p-n junction diode. A p-n junction diode and the forward bias voltage, the electrons and the holes will be combined in the junction region, which is called as active region. This recombination energy is expressed in terms of optical pulses. It is given in the optical frequencies, which is nothing but laser. But ordinary materials like germanium and silicon, they are not suitable for fabricating this SCL because they have indirect band gap. So a combination of third and fifth group elements like gallium arsenide, gallium phosphide, they are suitable for fabricating this semiconducting laser. In addition to this, you need a high optical power output efficient because the laser should be guided properly and you need almost maximum efficiency. So the condition here is the recombination region called active region should be made small. It should be very thin so that it should be comparable with the recombination of size of electron and hole. So active region is very small. And one more thing, all charge carriers should be guided into this region. So the recombination takes place in the thin region. At the same time, after recombination, whatever amount of light energy is produced, that also should be guided properly in this active region. So to achieve both simultaneously, that is confinement of charge carriers as well as the optical power output, you need a active region should be very thin. A ordinary PN junction cannot achieve this. So to get these two conditions, to get a proper active region, a double heterostructure is used for the fabrication of SCR. So in general PN junction diode, a p-type material and n-type material are sandwiched. But here in the heterostructure, that previous one is called as a homostructure. In heterostructure, it consists of two or three more layers of p-type materials in one side and two or more layers of n-type in the other side, which are sandwiched, which is called as active region, which is called as heterostructure. Sorry. And SiO2 isolation is made to prevent electrical spark between P and La because heavily doped materials these are. So to avoid electric spark, some SiO2 metallic isolation is made so that it is free from this electrical spark. So this is the construction of a heterostructure semiconducting laser. So two things to be achieved simultaneously. One is in the recombination region under forward bias voltage, which is called as active region or depletion region. All of charge carriers should be present. They should confine in the active region. They should not scatter. And also, after recombination, you should get light, which is also guided properly. So simple PN structure cannot achieve this. You need a heterostructure in which you have a series of p-type materials at one side, a series of p-type materials at another side. Both are sandwiched together, and SiO2 isolation is made to prevent electric spark. So this structure, which is called as a heterostructure. In the right side diagram, you can see that it is a series of p-type and n-type material. AuGAS is given, PGAS, and in the same way, n-type materials are also there, and it is polished and a metallic metallic coating is done to give certain contact for this. All these arrangements can be taken so that you can see emitting region. It is represented with a red zone, small active region. In this region only, the charge carriers will recombine from P side and N side. At the same time, this recombination energy comes in the form of optical pulses. Both will achieve simultaneously by fabricating this active region. So, heterostructure is used in P junction diode structure, which is a homo structure. Okay, is it clear, students? Then finally, the working of this semiconducting laser. So this double heterostructure of differently composed semiconductor layers achieve both the carrier and the optical confinement in the central active region. That's what I have explained. So charge carriers will confine to the active region. At the same time, after recombination, the optical power output also confined to the active region and it is carried properly by this active region. For this, you need a series of p-type with different band gaps and also different refractive indices, both p-type and n-type. So the difference in band gaps, they are selected in such a way that charge carriers should conform to the active region, and the refractive indices for the p-type and n-type materials are selected in such a way that after recombination, because of the values of the refractive index, the light output can be guided properly. So the selection of material is very, very important here. They are selected in such a way that both the carrier and the optical confinement should be done in the central active region. So this is in this way a semiconducting laser is fabricated. And as we have discussed in the Ruby laser and the gas laser, three important parameters are required. One is active medium, second one is pumping source, and third one is resonance cavity. So here in the active medium, it is highly doped gallium arsenide diode, if you take this one. And also the active region can also be considered as an active medium because there the recombination of electrons and holes takes place under forward bias voltage and produces laser light, the recombination energy. And the thickness of the depletion layer is very small of 0.1 micron. I said just now, a thin layer should be required because both the carrier confinement and the light confinement should be made only in the central active region. It should be made so small, which is of the order of 0.1 micrometer. Micro is 10 to the power of -6. So forward bias voltage is used as a pumping source. So whenever the heterostructure is subjected to forward bias voltage, then the conduction electrons will be injected from N type and the holes from the P side, and recombination of holes and electrons in the depletion region or junction region takes place. And once an electron and the hole recombine, the recombination energy, because these are direct band gap materials, it can be converted into straightaway optical pulses. The absorption of lattice ion is very small here, so it produces light. So the two phases of the semiconductor, because the light should be guided properly, the two phases of the semiconductor which are perpendicular to the junction, the phases of semiconductor are arranged in such a way that they are perpendicular to the junction plane, make a resonant cavity. So the top and bottom phases of diode which are parallel to the junction are metallized. So to make external connections, so connections can be given, they coated with some metallic elements, and the front and back faces are roughened to suppress the oscillations in unwanted direction. That means in those directions, the output laser beam cannot escape. So in this way, the diodes itself, they are coated with the metallic elements, and also they are roughened to suppress the oscillations in unwanted direction. So these precautions can be taken, and whenever the junction is forward biased at low voltage, whenever small voltage is given, the electron and the hole recombine and cause a spontaneous emission. Initially, what happens? Small number of electrons and the holes, they will be recombine and give the produce spontaneous emission, because the electron in the conduction band coming to the valence band by emitting energy. So when the forward voltage reaches a threshold value, then carrier concentration rises to very high value. So because of this, the region D, which is the depletion region, it has more number of electrons in the conduction band, at the same time large number of holes in the valence band. So in this sense, population inversion is achieved. Large number of electrons are available in the higher region, and population inversion can be done, and the electrons straight away under forward bias voltage they recombine with the holes. This recombination of electron and the holes leads to spontaneous emission. Again, the emitted photons they interact with the electrons in the higher energy level, so that stimulation emission starts. And finally, this gallium arsenide produces a laser light of 9,000 angstroms in the infrared region. So depending on the material, lasers of different. In the first slide I have shown the different colors of lasers will be produced based on the metallic content. Because at certain specific frequency, a composition. So based on the response, you will be getting a laser of particular frequency. So in this way, a semiconducting laser can be produced, and which serves for many applications. This is the construction and working of a semiconducting laser. Have any doubt, you can ask. In brief, if you want, I'll explain once again. Lot of theories involved in semiconducting laser. That's why I took one complete period to the semiconducting laser. Is it okay? Shall I explain once in brief? Students? Somebody respond, boys? You're listening or you're in lunch already? Yes?
Yes, sir.
Yes, sir.
Shall I explain or is it okay?
It's okay,
Girls?
sir.
Okay, girls? So you need, I will have prepared this PPT as per the exam point of view. The same you can, in the first slide you see at the right the top, different semiconductors lasers are produced, different colors on certain frequencies. So what is the principle behind the semiconducting laser? We should explain first. It is a p-n junction operating the forward bias. Under forward bias, recombination of electrons in the holes takes place, and this recombination energy comes out in the form of optical pulses. This is the principle of semiconducting laser. And ordinary semiconducting materials, because they have indirect band gap, they cannot give laser because the recombination energy goes to the lattice ion. But a combination of third and fifth group elements will work. The recombination energy is straight away converting into optical pulses. So they produce laser. The examples are gallium arsenide, gallium phosphide, etc. But here also the junction region or depletion region should be made thin, because both the carriers and the optical pulses should confine in the active region. A simple p-n junction structure cannot achieve this. You need a heterostructure. Heterostructure, you have a combination of p-type materials at one side, combination of n-type materials at another side, having different refractive indices and different band gaps, and the silicon isolation is made to prevent electric spark. So this heterostructure, the difference in band gaps confine the charge carriers in the active region, difference in the refractive indices confine the optical power output. So two things can be achieved simultaneously by taking a heterostructure, and the active region is the depletion region or gallium arsenide diode. The thickness is of the order 0.1 micrometer. And pumping mechanism is it can be done by applying forward bias voltage. So once voltage is given, electrons and holes will move in the respective directions, and the recombination of charge carriers takes place, and optical pulses are generated. And the junction diode is coated with the metallic oxides at the top and bottom, so that we can give metallic contacts, and the either sides they are roughened so that the light which is produced cannot scatter. So these things can be done simultaneously. And when small voltage is given, small recombination takes place, in the spontaneous emission, very few number of photons are released. But as high voltage is given, then the recombination becomes fast, because more number of electrons will be there in the conduction band, more number of electrons will be there in the valence band, top of the valence band, and population inversion is achieved, and electrons drastically they recombine with the holes by emitting radiation. Photons are released. These photons interact with the electrons in the conduction band. Few more photons can be released which are coherent. In this way, a laser beam is produced in the active region because of the recombination, and it produces a laser light of 9000 angstroms in IR nature. So this is the construction and working of semiconducting laser. And coming to applications, the applications are very wide for laser. Some I have displayed here in the defense and security, marking targets, guiding in the missile technology. These are very missiles, electro-optical countermeasures, blinding troops. So there are many applications as per the defense and the security is concerned. In the medicine, bloodless surgery, laser treatment, all you know, even for optical surgery, ophthalmology, kidney stone treatment, it removes the stones present in kidneys. Even for dental surgeries, neurology, tissue repairs, cosmetology, this laser treatment is very popular in medical engineering. And in the scientific also, laser fingerprint detection, cosmic science, spectroscopy, because laser spectroscopy, all ordinary rays are now they are replaced with this laser scattering microscopy, metrology. There are many applications, and as you know, consider this commercial and entertainment laser printers, all printers what you are using, optical discs, barcode scanners, thermometers, laser pointers, 3D holograms, laser light shows, decoration. All the bulbs are based on this laser principle only. So there are many applications of this laser, and a few more are mentioned here. CD-ROM disk reading. Previously, note you are using memory sticks or pen drives. Previously, CDs are there, and they read by a laser only. And optical fiber communication, and also aeroplanes are equipped with the laser radar. And tattoos, you know, the removal of tattoo can be done by using laser. And the principle behind DVD players, DVD readers, they made with this laser only. All these video games. So there are many applications of lasers. In the flaws in metals you can find. In the holography you can use these lasers. So like that, now in the world growing technology, the lasers are playing a very important role. And in the present chapter, we have discussed what actually laser and what are the three mechanisms: induced absorption, spontaneous emission, and stimulated emission. And Einstein coefficients are the postulates of Einstein and the relation between Einstein coefficients. Finally, by taking Boltzmann distribution law, you can relate the Einstein coefficients. Then the principle of laser and the components required for producing laser and the types of laser: ruby laser, helium neon laser, and semiconductor laser. Construction and working principle of laser we have discussed. And finally, few applications of laser also we have discussed in the present chapter. If you have any doubts, you can ask. Yes, students, is it okay? Semiconducting laser?
Sir,
Yes.
why krypton and argon are not used in lasers, sir? Like helium and neon.
It depends on. So what happened actually is the neon is not, if you give voltage to the neon atoms will not react. They won't excite because of the energy levels and the occupation of electrons in different orbitals. So because it is a very micro level interaction, and the helium neon also it's an indirect process. Initially, by giving discharge, helium atoms are get excited. Now, the excited helium atoms energy is equivalent to the energy levels of neon which are at the ground state. That's why they interact so that neon atoms go to their excited states. But even if they apply very high pressure, probably argon also can produce. But you should go to the logistics of that argon, what actually the structure, which another mixture probably they can interact with argon. And in the commercial productions, the commercial logistics can also be taken into consideration. So whether it is viable or not, I don't know. But the thing is, this helium neon laser, now it is gas laser is a outdated one. Initially, it is a ruby laser. There are certain drawbacks. Then gas laser has come. It has some advantages. Again, the cost wise, it is a little bit. You need a quad tube, and you should take the you should maintain the pressure. everything can be taken into consideration. So how much you are spending and what laser is coming finally, this cost logistics can also be taken into consideration. And again, after this diode technology, semiconducting laser has come. Even in Chiragali and in Koti, you will be getting small pointer type semiconducting laser will be there. Small cell will be there. If you on it, you will be getting laser. So this is as simple as such. So those days, probably during the experiment, they observed that the combination of helium and neon is probably it is convenient as per the commercials of taken into consideration. I think so. Nobody has tried with argon. You can try. I don't know. Yes. Anyone else? So I think in this sense, the semiconducting major chapter is completed. So many are joining at the end. When I have suddenly verified there are only 36 to 38 students and 12 students came for attendance. 61, 62, they are not there in the beginning. What 61? Where are you? Simply for attendance you are coming? Respond. 61.